So in this screencast, we are going to look at the periodic table and some periodic trends. Chemists for a long time had noticed that the elements exhibited what are called periodic properties or repeating patterns. Okay? Specifically of behavior when the elements were arranged in order of increasing mass. Now, that was studied by several 19th century scientists, and they would create tables of elements that were arranged in these patterns based on similar chemical properties. The most successful version was published by a guy named Dmitri Mendeleev. And there's a picture of him right there. He was a Russian chemist, and it was published in 1872. And what made his periodic table different is he ordered the elements according to atomic mass and then arranged them into columns. And he arranged them into columns based on similar chemical behavior. Right? Now, he also recognized there were elements that were that needed to be discovered, and so he left empty spaces as needed. And based on the periodic nature of the chemical properties, he was able to predict the masses and a lot of times the properties of these unknown elements. And then people would come along and discover them, and he'd be pretty close. So he really put together what we would consider the foundation of our periodic table now. I showed you this in one of our previous chapters, but I just want to show it again because I just think it's a beautiful rendition of the periodic table. When we look at the periodic table, the periods are the horizontal rows, the groups are the vertical columns, and in the groups, these contain elements with similar properties. And we've already seen things like the elements that are in this group all form a charge of +1 when they form ions. And so we can go ahead and begin to use these properties. Now, again, I want you to notice that the metals are here in kind of this tan color. The non-metals are here in this green color, and the metalloids are here in these purple colors here. When we look at periodic tables, there are a lot of different broad categories for us to use. And so the next two, we're going to look at some more specific naming that we see in the periodic table. And I chose this because I wanted you to see the lanthanides and the actinides here, and that these are metals. So I like this image because it shows you that these are popped out and these are still metals here. And so they fit in here. The reason they're popped out in most periodic tables to be down here at the bottom is because they would really stretch it out. It would become very awkward. So there are a lot of times here at the bottom. The top one here are the lanthanides. The bottom here are the actinides. And sometimes these are called inner transition metals. Okay. The other groups of the periodic tables that we have, lots of different ways to kind of divide this up. We can divide it up into main group elements, which are representative elements. They're in groups 1, 2, 13, 14, 15, 16, 17, and 18. We've already talked about some of the things here, particularly like valence electrons, to be able to identify in the main group elements. And then here are the transition metals. Now, transition metals are really interesting. They can have kind of multiple charges. And so we'll talk about those later when we get on to naming. Now, when we talk about the groups, some groups have specific names. For example, this group 1 here are named the alkali metals. Group 2 here are the alkali earth metals. Remember, we've already talked about transition metals and intertransition metals. These are the noble gases here. These are the halogens. And sometimes some books will have 16 here as the chalcogens. All right. So let's talk about how we can use the periodic table. So we can use the periodic table not only to predict things like valence electrons, but also to predict things like the atomic radius. So when we talk about how big atoms are, that's our atomic radii, okay? And what we find is that the atomic radius increases as you go down a column, right? So it increases. And it decreases as you go across the row. Now, you'll see this pop up, and you can do this in a lot of different ways, but I like to say it increases as you go from right to left, okay? I just like to think of it that way because I like to think of, hey, look, cesium down here, he is huge, right? Compared to helium up here, which is really, really tiny. My suggestion would be when you get your exam, and I'll hand it out, I'll give you a periodic table to go ahead and just write, size. A lot of times we talk about atomic radii as the size, but the size increases down and the size increases across. And so that's kind of the questions you'll be asked is, which is bigger, bromine or iodine, right? And you'll say, oh, well, size increases as you go down, so iodine's going to be larger, right? Now, it's never my intention to be tricky, so I don't plan on doing ones that are kind of catty corner to each other. So you're like, oh, this one's one over, but this one's one down, right? I like to choose things that are really cut and dry. Now, these are uncharged atoms. Let's talk about what happens when you gain an electron or you lose an electron. So cations, you've lost electrons, we've formed a positive charge, and so it should make sense if we've lost something that the cations are going to be smaller than the parent ion. Right? And so when we look at this, we have an uncharged lithium here, and then we have a lithium that has lost an electron, and so it's gotten smaller. Okay. Same thing with sodium. We see the same trend with magnesium. And with anions, we've gained an electron, and so now it's going to get bigger. So anions are larger than the parent. I said parent ion up here, and I even wrote it, and I meant to say atom, the parent atom. So make sure you correct that. So when you look here at sulfur, now, right, we've gained 2 electrons, and we're much bigger. Okay, so that's something else we can predict, right? That's called a periodic trend because it's something that we observe broadly over the periodic table. Now, there are 2 other trends that we can observe and are talked about in this chapter. One is ionization energy. Now, ionization energy is the energy required to remove an electron from an isolated atom. And so a lot of times visually this is shown as the atom over here by itself. There's an arrow, and then now the atom has a plus charge because we've removed 1 electron, right? And sometimes the one is shown and sometimes it isn't. But we've removed that electron. And so this is the energy required here. And what we find is that ionization energy, and I'm going to abbreviate that as IE, decreases down a group. And so if we look here, this is just a different rendering of the periodic table. It's showing like the ionization energies are shown here. And what you could see is you go down this group, right? You're seeing we're decreasing in ionization energy. And so the other thing that we see is that ionization energy increases across a period from left to right, right? So we have an increasing ionization energy there. Now, we also have electron affinity, and this is, and I abbreviate that as EA, so let me spell that out. We have electron affinity, okay? And this is the energy change when a single electron is added to an isolated atom. And so, for example, you have bromine, you add an electron, and now you have bromine minus, okay? Electron affinity decreases down a group roughly. Now there's some exceptions here. And then it increases across a period from left to right. So hopefully in this screencast you are now familiar with the periodic table, and you can use the periodic table to predict different trends that the atoms, different trends of atomic properties.